Hello everyone. What if I told you that AI doesn't actually understand a single word you type, and yet it can explain you quantum physics, write code, draft business strategies, and answer complex questions in seconds? How is that even possible? When we interact with AI, it feels intelligent, it feels aware, sometimes it even feels human. But inside a large language model, there are no thoughts, no meanings, no comprehension in the human sense. Instead, there is a precise mathematical pipeline. Words are broken down into tokens. Tokens are transformed into embeddings. Embeddings become vectors in high dimensional space. And those vectors are searched inside massive vector databases to retrieve meaning based purely on distance. What feels like conversation is geometry. What feels like reasoning is probability. And by the end of this session, you will understand something most AI users never realize. How language becomes numbers, how numbers become geometry, and how geometry becomes intelligence. Stay with me because once you see what's happening inside an LLM, you will never look at AI responses the same way again. What are tokens? The first thing AI does is break your sentence into smaller pieces called tokens. These tokens are not always full words. Sometimes they are fragments of words. Sometimes they are punctuation marks. The model's vocabulary determines how the split happens. For example, the word unbelievable might be divided into an, believe, able, and the exclamatory mark. Humans read sentences for meaning. Large language models process tokens sequentially one at a time. Each token becomes a unit of computation. The sentence as a whole is temporarily dismantled so it can be mathematically analyzed. Tokens are the basic processing units of language in AI systems. They are the building blocks that everything else depends on. From tokens to embeddings. However, tokens are still text, and computers do not understand text in the way humans do. So each token is converted into a list of numbers. This list is called an embedding. An embedding is not just random numerical data. It is a structured representation that captures relationships and contextual meaning. Words that are used in similar contexts tend to produce similar numerical patterns. For example, doctor and hospital will generate embeddings that are mathematically closer than doctor and mountain. At this stage, language has been transformed into vectors of numbers. Meaning is no longer expressed in definitions, it is encoded as relationships in mathematical space. Tokens become numbers, numbers begin to carry structured meaning. What is a vector? The list of numbers, the embedding, is mathematically known as a vector. You can think of a vector as a coordinate in a multidimensional space. Not two dimensions, not three, often hundreds or even thousands. In this space, every word occupies a position. Words with related meanings appear closer together. Words with very different meanings are positioned further apart. For example, the vectors for king and queen will be close to each other, whereas the vector for dog will be somewhere entirely different. In artificial intelligence systems, similarity is not philosophical, it is geometrical. Distance becomes measurable meaning, and once meaning is represented as position, it can be searched. What is a vector database? Now imagine millions or billions of these vectors stored in a system. That system is a vector database. Unlike traditional databases that search for exact word matches, a vector database searches for similarity in mathematical space. When a new query is converted into a vector, the system looks for stored vectors that are closest to it. If two vectors are near each other, they likely represent related ideas. This is how modern AI search works. This is how recommendation systems understand preferences. This is how retrieval augmented generation provides relevant context to language models. The system is not scanning for identical phrases, it's scanning for proximity in meaning. And that proximity, it retrieves knowledge. Now let us look into an example. You type a simple question, what is quantum computing? To you, the sentence carries curiosity and intent. You're asking for clarity about a complex concept. You understand what you're asking. But inside the AI system, something very different happens. The model does not see a meaningful question. It does not recognize curiosity and it does not interpret intent. What it receives is simply a sequence of characters that must be processed mathematically. The first transformation happens immediately. The sentence is broken into smaller units called tokens. These tokens might be full words, fragments of words, or even punctuation marks. So your single sentence becomes a sequence like what is quantum computing question mark. At this point, the idea of a sentence no longer exists. There is only an ordered stream of tokens that the model can compute on. But tokens are still texts, and computers do not understand text. They operate on numbers. So each token is converted into a numerical representation called embeddings. What becomes a list of numbers? Quantum becomes another list. Computing becomes another. Your question has now been transformed from language into mathematics. Those lists of numbers are not random. They represent positions in a high dimensional space, often hundreds or thousands of dimensions. In that space, related concepts are positioned close together. The numerical representation of quantum computing will sit near qubits and superposition because their pattern of usage are statistically related. In artificial intelligence, similarity is not a feeling, it is a measurable distance. Now, here is something most people don't realize. Long before you asked your question, the system had already processed vast amounts of information. Documents were divided into chunks, converted into embeddings, and stored as vector inside a vector database. That database does not just store text, it stores meaning as geometry. When your question is converted into its own vector, the system searches the geometric space. It doesn't look for exact keyword matches. It measures distance. It identifies stored vectors that are closest to your questions in that multidimensional space. The closest vectors corresponds to the most relevant ideas, explanations of qubits, descriptions of superposition, comparisons between classical and quantum computing. This process is called a similarity search or the nearest neighbor search, and it is the foundational about meaning alignment, not word matching. The retrieved information is then provided back to the language model, where the vectors are converted back to tokens and predicts the most statistically likely next token at each position. Quantum computing is becomes a type of computing becomes that uses quantum bits. Token by token, probability by probability, the system constructs a complete answer. What feels like understanding is actually a chain of transformations. Language into tokens, tokens into numbers, numbers into vectors, vectors into geometric search, and finally probability driven generation back into language. And from that purely mathematical pipeline, an intelligent explanation emerges. One that sounds intelligent, structured, and meaningful. That is the journey your question takes inside a large language model. By the end of this journey, something remarkable has happened. Human language has been transformed into numbers. Numbers have been organized into geometry. Geometry has been used to retrieve relevant knowledge. And from that mathematical foundation, AI produces responses that feel intelligent, coherent, and contextual. What looks like understanding is actually precision mathematics operating at massive scale. And that transformation from language to geometry to response is the real story behind modern AI. Thanks for watching. If this video helped you, hit like, share it with friends, and subscribe to Decode Bro for more insightful content. Stay tuned for the next episode. Until then, take care.